Sir, namaskar. Rajeevan sir, namaskar.
Namaskar. Namaskar. Dr. Patnaik, you will be sharing my presentation. I have to share from here.
No, that's because we are ready for that. As you suggest, we can share from our end.
I think I will try to share. If it's not, I'll just spend some few seconds.
Yes, sir. No.
If it's not working, then you can.
Sure, sir.
I made small changes. So.
Okay, sir. No problem.
Apart from that, handling the slides from own side has advantages.
So shall I start?
Just a minute, sir. So we have till 1 or 2 minutes till there.
Sure.
I think you should first try to share. In case of problem, Patnaik will display.
Yeah, we'll do that. Our people will do that. Yeah, it is sharing very well. No problem. Yes, sir.
Yeah.
You're able to see?
Yes, sir. Yes, sir. Yeah, it is. Yes, perfectly all right. Yeah. So I think we can start now, sir. Now? Yeah. So good evening, good afternoon, good morning from where depending on from where you are watching. So now this is our local afternoon session, invited session. So may I now request Professor S.K. Das, sir, to kindly chair this session to give a brief introduction about Professor S.K. Das. Dr. Das entered Math Science in 1975 as a PhD student in the PRL, that Physical Research Laboratory, Ahmedabad, after an illustrious academic career in physics. Professor Das superannuated from IIT Delhi as professor and head in the Center for Atmospheric Science and is currently associated with the Center of Atmospheric in Climate Modeling as visiting scientist, Center of Excellence. In his 47 years of experience in teaching and research, Professor Das has successfully supervised 20 PhD, 16 MTech, MPhil, MSc, MCA students. Professor Das is actively involved in R&D activity, including 35 sponsored projects. His main area of interest are interannual variability of Indian monsoon, climate modeling, climate change studies, and HPC, high power computing in environmental sciences. Professor Das has illustrated 140 plus referred papers in journals of repute. He has been deputed to many reputed institutions across the world as visiting scientist. Professor Das has been the fellow and president of Indian Math Society, fellow of Royal Meteorological Society, UK, and the member, the Indian Academy of Sciences, India. Over to you, sir.
Thank you, Dr. Patnaik. First of all, I welcome all of you to this important session of IWM-7. In fact, it is continuation of the same session, subseasonal to seasonal. And as you know, it's a very, very not only scientifically challenging, but also of a lot of societal benefits and of operational importance. And in this session, there are 4 distinguished scientists from across the world, from India, China, Japan, and they have contributed to this field immensely. First speaker will be Dr. M. Rajeevan, who is very much well known across the world. They have prepared this slide to introduce Dr. Rajeevan to the audience, but he is well known and it's not necessary to really speak much about him because he has contributed immensely to the Indian monsoon, and especially the data, this grid data, the concept-wise and generated this, which has been helping a lot of scientists across the world. And he has also worked on the extremes of Indian monsoon, monsoon variability, signal forecasting, climate change and extreme weather events, prediction of mesoscale systems, and development of climate data sets like gridded rainfall data, as I told. He was a member of the WCRP Cliver Asian Australian Monsoon Panel and presently a member in the research board of WMO. He has more than 140 research papers, and presently he is working as MOES distinguished scientist after his superannuation as Secretary to Government of India in the Ministry of Earth Sciences. He was there during 2015 to 2021, and he has significant contribution to Monsoon Mission and Deep Ocean Project, which is coming about in future. A lot of contributions he has made. Now I request Dr. Rajeevan, instead of wasting any more time, to speak on this Indian Monsoon Mission.
Thank you, Professor S.K. Dash and Dr. Padnaik for introducing me. And I'll be giving a talk about 15 minutes or so. First, let me share this presentation. Yeah, so I'll be talking basically on Monsoon Mission, which India has launched a few years back, and what are the achievements in terms of short to medium range weather forecasting. So that I'll be briefly I'll be talking about with some good examples. And as all of us know that Indian monsoon prediction is very important because monsoon rainfall amounts to 80% of annual rainfall, and economy, life and property in the region are vulnerable to significant variability of monsoon on different time scale, day to day, intra-seasonal, intra-annual. Until 2009, IMD is the is the main organization, the responsible organization for issuing weather and climate forecast and warnings. So IMD has been issuing short-range forecasting using some regional models, etc. While the medium-range forecasts were issued based on a very low resolution global NWB model like T180 or so, T80 or so. The general operational dynamical system for extended range forecasting system, extended range prediction was not at all there. It was not existing. And seasonal forecasts, of course, we have been India has been doing it since 1886, but mostly it is indigenously developed based on indigenously developed statistical models. So when there was a need to for the country to develop substantial capability in terms of monsoon prediction, because we know that monsoon prediction in all time scales are monsoon prediction in all time scale is very, very important, and for agriculture, water resources, the disaster management, etc. So in 2012, the monsoon mission was launched with the ultimate aim of improving forecasting in all time scales. And the first phase was for about 5 years, 2012 to 2017, and second phase was about 2017 to 22, and third phase, I think this is being launched from this year. And the purpose is to improve the forecast. So we invited the proposals from different organizations, different international or institutions, and we invited the participation of leading scientific meteorologists and modelers who are interested in monsoon research from different countries to participate, and we provided them financial support. And so far we have funded about 66 projects, and out of that, half of them are more than half of them are from India, and about 30% of projects were given to US scientists in US. About 20 projects were given to US projects, and 4 projects were given to UK, Australia, Japan, France, Canada, and the UAE. And so all this was a huge collaborative program involving Indian scientists, Indian academic institutions, MOES institutions, and also international participants, international researchers. And ultimately, we could really do an excellent job. And the ultimate aim, result was that India could develop a full-fledged forecasting system, almost like a seamless forecasting system, dynamical prediction system right from short range forecast to seasonal forecast, even on climate change projections, etc. So we have a model from starting from 1.5 kilometer regional model, and we have a 4 kilometer regional model based on UK Met Office. So we have two systems, one based on UK Met Office systems models, and another is based on Ensembles models. So we have two different systems existing, and all these models are being used by IMD for their day-to-day forecast. Yeah, in terms of global model, we have about resolution of T1534. It's about 12 kilometer model, global model, and we use both deterministic as well as ensemble prediction system. So we have two ensemble prediction system of about 40 ensembles, and also we have a deterministic model of 12 kilometer. Then for extended range forecast system, we have a coupled models starting from 32 kilometer model. And we also have an Earth system model. First time for the country, we have developed a system model which is of a coarse resolution, but then it is also based on the CFS model. So we have a suite of for air pollution, especially for predicting air pollution over Delhi region. We have a very high resolution 400-meter Delhi air pollution prediction model, which is operational now. So, and also 330-meter Delhi fog prediction model. So right from a small, very high resolution, we have starting from a very regional localized model to global models. And so data assimilation will be a part of all this initiative, and we have spent a lot of time and investment. We made a lot of investment in improving a data assimilation. One good example, so we could get good connections with the EUMETSAT. We could get good connection with Japan Meteorological Agency and Chinese Meteorological Agency, and we could derive all the satellite data which are available now. And we have improved our data inputs into the models. And one good example is the ALUS winds. You know that it has come. The satellite provide you the vertical profile of winds, especially in the upper troposphere. And this we started assimilating to the model. And it is a really, and I was told that it's going to be a big breakthrough in terms of data assimilation. This winds, because we badly wanted the vertical resolution, so the vertical profile of the winds. And this is a good example of how Cyclone Takute formed in the Arabian Sea was predicted using this kind of data assimilation. And if you really see the skill of improvement in NWP skill over the Indian region, you can see that starting from 1999 up to 2022 or so, 21 or so, there's a substantial improvement. Especially you can see the substantial improvement from almost from January 2012 and later from January 2017 onwards. There's a substantial improvement, mainly because we try to introduce many new models with very high resolution, and a lot of data have gone in for data assimilation, and also some improvement in physics, model physics, etc. So ultimately, there's a substantial improvement in NWP skill over the Indian region. And this is a good example from when we migrated from T574 model to T1534 model. And there was substantial improvement in just 2 days with the forecasting skill. And for example, the skill of the GFS T574 with the 3-day lead, it's shown as a blue dotted dashed line, is now extended up to 5 days. And so now the same skill we can even achieve up to 5 days. So there's a substantial 2 days substantial improvement we have achieved by simply moving from 1574 to 1534. But of course, with a lot of data assimilation and also improvement in physics. And this, I'll give you some few examples now from these models. This one monsoon heavy precipitation occurred in last year, 14 September 2021. The top 3 panel, left-hand side shows the GPM rainfall, and the right-hand shows the probability of 90th percentile in the top, and bottom is 95th percentile up to 3 days lead. And you can see that beautifully the model is, the ensemble prediction system is reproducing the probability, very high probability, 1 over Gujarat and 1 over eastern parts of central India. And this is another example of last year, 31st December 2021, Chennai region was affected by heavy rainfall and there was a lot of casualties. And this the ensemble system could provide some kind of a signal for extreme rainfall over this region, even up to 3 days in advance. And this is a beautiful story of Kerala rain. You all may be remembering 2018 and 19, we had consecutively 2 years, we had heavy rains and floods and there were a lot of casualties. The top one shows the 18 and the bottom one shows the 19. And the blue line shows the observed rainfall for different dates. And the first one is for 1 standard deviation, climatology plus 1 standard deviation. Second one is climatology with 2 standard deviation, and the right one is climatology with 3 standard deviation. You can see in the first year, 2018, the model could give up some kind of probabilities for 1 standard deviation extreme rainfall, but 2 and 3, there's nothing, no signal. Whereas in the 2019 case, even in 2 standard deviation, there was a signal of extreme rainfall, and also to up to 3 standard deviation. There is some kind of indication, even though there are small shift in the days of extreme rainfall. So the extended range prediction system is providing a very useful information about the probabilities of extreme rains over India. And this is a deterministic forecast, but this is from 4 kilometer NCMR-WF model. This is of Uttarakhand rainfall recently. And the top left one is observed and remaining are forecast. You can say day 1, day 2, day 3. And of course, the model was picking up good rains, but only thing is a little over prediction over specific regions. And IMD's tropical cyclone forecasts are well known, and India is well known for now most accurate cyclone forecast for last many years, and starting from cyclone Philin. And this is a typical example of Amphan, which caused May 2020. And the story goes, the story clearly says that the ensemble prediction system gave a better kind of a forecast for its track as well as the landfall, and then a deterministic forecast. So ensemble prediction system is really providing useful information or useful hints about the tropical cyclone tracks as well as the landfall. So the improvement in our tropical cyclone forecast, of course, it has a lot of different reasons for that, and one major reason could be the improvement in the models and adoption of we adopted a very high resolution model with a lot of data simulation that were providing a lot of important guidance for tropical cyclone forecast. Plus IMD also using their own skill for improving their forecast. And even landfall is for Amphan case, it was up to 10 kilometer error only up to 60 hours in advance. That's a very remarkable achievement in terms of cyclone forecast. And we also introduced during last few years, we introduced the heat wave forecast. Heat waves are very important in the country. And what we try to do is we started with a seasonal forecast of probabilities of heat waves. Then we started introducing extended range forecast, then short range forecast. So in the different time scale, we started kind of a seamless kind of forecast we started implementing, and we found this very successful. And heat wave forecasts are very skillful forecast. We could do it even up to 5 to 6 days, sometimes even 1 week before we could achieve it. And this is a good example of this year, March 2022. March is too early to get a heat wave, but this year, March, we had a heat wave, and the model could really predict this kind of heat waves, which is occurring too early in the season. And this is a good example. So heat wave forecasts are pretty good. And because of heat wave forecast, many state governments are now coming up with the heat wave action plans, and which they give it to the people, and we are able to save precious lives, many lives. As the death of the cost due to heat waves is basically decreasing with the time. And another important application is the quantitative precipitation forecast for river basins. The river-based flood is another important major extreme kind of natural disasters occurring over the country. And so this the left-hand side is the observed rainfall of 27th August 2020. And if you see the top panel is a forecast for different 5 days. And you can see that after 3 days or after 3 days, there's not much skill, because when you do a bias correction of the model, it gives you a lot of information even in 5 days before that kind of a heavy rainfall probabilities and heavy rainfall occurrence over that the river basins. It's the upper Mahadadi basin. And so this forecast guidance we are giving to guidance is given to Central Water Commission, who will be using this information for issuing flood forecast for river basins. So very successful story how our NWB modeling system has really improved, and we are able to give quantitative precipitation forecast I'm not saying everything is perfect. There are gray areas which I'm not really highlighting, but I should accept there are a lot of gray areas where we need to improve. And I'll briefly I'll mention cyclone warning forecast. We have improved substantially, and heavy rainfall warning. As you can see, the skill is probability of detection is going up. The false alarm rates are coming down, and so it's a substantial improvement in heavy rainfall warning skill. And even detection of thunderstorms in even 24 hours before, there's a high probability of 0.86 or so, and even 3 hours before using models as well as the Doppler weather radars also has improved. And heavy rain, heat wave warning skill, as I told, that substantially even up to 5 days before, we are able to predict heat waves very accurately. And another application is for the energy application. And also all of us know that we are India is pumping a lot of money in wind as well as solar energy. So this is the one product which we are generating for the energy sector. Different companies are asking for these products, and both IATM as well as WMO are providing this kind of very accurate forecast. Not very accurate forecast, but then a lot of issues, especially on solar energy during cloudy skies, etc. But then we are trying to improve further, and both solar as well as wind energy applications are plenty. And thunderstorm process, we introduced about a few years back, 2018. We had a huge thunderstorm activity. At least some thousands of people died, and it caused a lot of concern among the government, public, and also the policy makers. Then finally, we tried to improve our thunderstorm projects. We introduced thunderstorm detectors around the country. We have about more than 100, around 100 thunderstorm detectors are in the country now. Using that, we can really monitor how thunderstorm activities or lightning activities are happening. We developed a mobile app. We also improved our model forecast. We try to adopt very high resolution models. And this is a good example of 2019, 6th of April. And the top one, the left-hand side top one shows the thunderstorm activity where it happened, and the bottom one and as well as right one are the different kind of forecast, different kind of guidance of thunderstorm activity, which clearly depicts occurrence of thunderstorm. And another important application is the short to medium range forecast is the quality of air quality forecast. As all of us know, Delhi is very well known for poor air quality, and Prime Minister Office wanted us to develop a air quality warning system, warning system for Delhi, and which we could do it. Now we have two systems, one based on NGAR with the support from NGAR, with the collaboration from NGAR, and another one is using Finnish Meteorological Office. And we have two different modeling systems, and both of them are doing extremely well. This is a good example of how the IATM was collaborating with the NCAR, and this is the IATM system. And we have a regional model of 10 kilometer, which is downscaled up to 400 meter only for Delhi region. And reliable forecasts are being generated on air quality over Delhi. And in addition to that, we also provide kind of a decision support system for Delhi. And during winter, all of us know that Delhi airport is very was affected by fog events, and many disruptions of the aircraft flights, etc. happen. And so they wanted a special forecast for winter. So we have 3 different systems are now in operational. And aviation industry is making use of this. One is air quality, which is general Delhi public, and also decision-making system for Delhi, and also the winter fog experience. And another important achievement made by the Monsoon mission is the beautiful data sets, regional reanalysis data set which was developed with the collaboration from UK Met Office, and it's the Indian Monsoon Data Simulation and Analysis called IMDA. It's a paper is available, data are available, and I think it's 42 years of data of 12 kilometers horizontal resolution. I think people should be encouraged that people should make use of this data for their research. It's a beautiful contribution from Monsoon mission. Another is the Bombay flood warning system. And earlier we developed a system for Chennai. The similar system is now developed for Mumbai. And this model has different components. It makes you make use of rainfall, how much it is received, and how the river flow. There are a lot of small lakes there in Bombay, and also there could be kind of a tidal waves coming inside the city. So all these components are taken care, and it's a full-fledged dynamical prediction system has been developed for Bombay. We have issues for giving an accurate weather forecast, rainfall forecast for that Bombay region, which we are addressing. We are running a very high resolution NCMWF 4-kilometer model forecast are giving us inputs to the system, but there are issues. There are issues. We should accept that there are issues. And another important achievements we made is the observational campaigns. We did not only believe in improving models, we also believe that observations are very important, especially intense observational campaigns. So there was one Indo-UK monsoon mission campaign. I saw Andrew in the panel. So Andrew Trainer was also the main person who was from UK side, and he has written a small article in Clever Exchanges in November 2020. I think we should read. And I understand there are plenty of good research papers have come. It had three important components. One is on interaction of convective organization and monsoon precipitation in campus. And there was an aerosol experiment called Swami and a boundary layer experiment over Bay of Bengal is called Bobil. Another experiment was done also into US monsoon campaign. Just before this into UK, it started just before that. And the primary purpose of this campaign was to understand the ocean mixing process over the North Bay of Bengal, and very high resolution measurements were obtained, and a lot of modeling work also being done. Under the Indo-UK Monsoon Mission program, we could bring the UK Met-Office jet aircraft, research aircraft, and we could do a lot of aircraft observation for the first time in this country. After probably 1979 monarchs, we could do that. And the new experiment we are now proposing, joint experiment, is called ECAM-SAT. It's called Enhancing Knowledge of the Arabian Sea Marine Environment through Science and Advanced Training. And I'll stop with the two more slides. And as all of us know that we also need to improve the physics of the model. So we need a lot of observations of cloud physical processes, land surface process, cloud process, etc. So we are going to launch a research testbed over Bhopal. Bhopal is over central India, where all these monsoon lows and depressions form and pass on through this. It's a very beautiful site where we can put all kind of instruments and take observations. And this is going to be an international research testbed facility. And already workers, we got some land thanks to Madhya Pradesh government, and we have started putting this instrument. Another 2 years, this facility will come up as an international facility, and I request all the international scientists to make use of this facility for understanding the monsoon physical processes. And all this data will be shared internationally. And another investment we are making is for urban flooding over Mumbai. We are starting a very high resolution rainfall network over that region, and including we are going to set up intense surface observations, especially ARGs of maybe 200, 250 ARGs. In addition to that, we will be setting up 4 weather radars, X-band 4 radars, small scale, small range weather radars, and put together we will be able to generate rainfall values of every 15 minutes at every 5 kilometers or so. So this is the dream project, and of course there are small delays because of the COVID, etc. But by next year, this year monsoon, this network will be fully operational. And with this observations, we will be able to understand more about what kind of urban flooding can happen in Bombay. And along with the Bombay flood warning system, this data will be very, very useful. So with that, so this kind of initiatives also Ministry of Earth Science have launched. And with this, all these things, observations, modeling, everything, I hope that our weather prediction capability has improved a lot and will substantially improve further. With this, I will stop here. Thank you very much for giving this opportunity. Thank you.
Thank you, Dr. Rajeevan. You gave a very nice picture of the monsoon mission developments made in all fronts: data observation, data simulation, modeling, and operational forecasting. Now the presentation is open for questions, discussions. I don't find any chat question. Anybody can raise hand for a couple of questions. I don't find anything on the chat. Only one. No, I don't see.
Yeah, there is one from Andrew Turner.
Yeah, but that's I'm just trying to read it. Mr. Rajeevan is presently working as the that is on the on Dr. Rajeevan introduction. Then Andrew Tanner, no, I don't see anything on the chat. On my chat, I don't find. He is there, I think. He can ask.
Sir, one question is there from Andy Turner.
Yeah, maybe I'll.
Sir,
Can I speak the question?
I can say, yeah. He can ask, yeah. Because
Okay,
I don't.
I was just going to ask what does Professor Rajeevan think are the key research priorities that maybe we are not doing enough of already, or perhaps not even doing at all? You know, what are the priorities that we don't already have projects working on?
What was the question?
What are the key research priorities going forward, do you think?
Yeah. Key research priorities: improving model physics, that could be one, and improvement in data simulation. And another important aspect which we neglected, we have not been doing it, is the model, the post processing of model output. We always thought that model output is the actual forecast. So for the general public, IMD has to do a much intelligent post processing of data, NWP model outputs, before they can make it a product to give it to the public. So IMD is going to launch a kind of post-processing research initiative using artificial intelligence and machine language techniques. So we can derive much more useful information from model output instead of using rather raw output. So that is one area where IMD will be concentrating more, and IMD will be establishing more and more observations everywhere, including more. Another 20 Doppler weather radars are going to come, and we are not so good in model physics. We're doing, for example, very hardly a couple of people are working in model physics, especially physical parameterization schemes. We need to really do much more work on model physics, and we also need to adapt model techniques, parameterization techniques, stochastic process, etc., into the model. This is the one area where we will be working on that. So plenty of work to be done.
I don't find any other. There's something problem with my chat box, I think. Somebody has noted here that yeah, Andrew Turner, now I see. Now I can see Andrew Turner. Somebody, thanks for the nice presentation. That is Thierry Lafort. Thanks for the nice presentation. I trained IMD forecasters in 2020, and I can attest the great improvements that IMD has achieved in 1 decade for elaborating and delivering useful information. So it is one appreciation for the IMD. Okay, I think because of shortage of time, yeah, do you have to say anything now?
Thank you.
Yeah. So now, because of shortage of time, we can't really continue. So I thank Dr. Rajeevan. Let us thank Dr. Rajeevan for his very elaborate presentation. And now we go for the next presenter, next speaker, Dr. Qing Bao, who is a professor in the Institute of Atmospheric Physics in the Chinese Academy of Sciences. He obtained BSc in Meteorology and Nanjing Institute of Meteorology in 2002, and PhD in Meteorology, Institute of Atmospheric Physics, Chinese Academy of Science. Then since 1928, as a Geophysical Fluid Dynamics, Institute of Atmospheric Physics, Chinese Academy of Science. His research topics are primarily in climate system modeling, subseasonal to seasonal prediction, and seamless prediction. He is the recipient of many prestigious awards, like 2011 G. Yibing Young Scientist Award, 2012 IAP Science Innovative Award, 2014 Tsinghua University Insport Group Computational Art Science Talent Award, 2015 ACE Esteemed Paper Prize and IAP Science Innovative Award, 2016 Tian Star Awards of Excellence Application. Dr. Bao will speak on the monsoon information and prediction for societal benefit. Dr. Bao, please, on stimulus prediction system. You have shared your, you can share your slides now. Yeah, thank you. We can see that. Please continue.
Thank you very much for your introduction. And it's my great pleasure to introduce our prediction system and some application in Asia monsoon region. I'm Qing Bao from IAP. Here is the outline of my talk. First is the introduction. As we know, the seamless prediction is cover a lot of time scale from the day, week, month, season, or even many year, longer time. They have a lot of application field that focus on the many time scale. But as we know, there are a lot of gaps between the traditional prediction system, like the S2S is fill the gap between the weather prediction and the climate prediction, and another gap between the interannual and the interdecadal prediction. That means the seamless prediction will cover many gaps between the previous prediction system. As we know, what are we gonna predict? We are not predict 1 year later the temperature or the precipitation, but we should focus on the extreme part like tropical cyclone, heat wave, drought, and flood. Okay, this is the current operational subseason to decadal prediction system already noticed in WMO. Because first you look at subseasonal prediction system, there already be 11 prediction group. Fortunately, we are the last one to participate the S2S project. There are 13 seasonal prediction system. I think most of operational center, they have their own seasonal prediction system. But in IPCC or CMIC, the 15 centers, they submit their decadal prediction. I think the decadal part be renewed every IPCC report, maybe 5 or 8 years. But for Met Office, they renew their results every year. Opportunity and challenge for subseason to decadal. I think in current world, especially in China, we have quite good HPC. That means we can run the model with very good computing resources. But the challenge part is that we need a good models because there are a lot of uncertainties from like cloud convection or topography issues. Even with the biggest computing resources, we cannot solve like precipitation or extreme part. That means we have opportunity, but challenge is still there. Okay, here's a climate system model I'm going to introduce today. It's called FGOES, F2 versions. In this climate system model, we predict several IPCC or CMIC experiments. We propose a new scheme. We call it the RCP, it's Scale Wellness Convection Scheme. We try to resolve convective precipitation in the model physical package. It's a fully coupled model, including not only atmosphere components, also ocean part, sea ice, and the land. We use FV3 dynamic core because it's running very fast. Okay, and you look at the model performance, and this scheme is quite good at the extreme part, especially over the south slope of the Tibetan plateau regions. If you look at extreme precipitation from the observations from the station data, it's up to 150 millimeter per day. Extreme parts model did a pretty good job to capture this extreme parts. And look at MJO, another important extreme phenomenon. But look at the middle one. I adopted figures from the recent publications. This model actually is a previous version from our CMIP5. Without this RCP scheme, you see the MGOs propagate to the wrong direction. But in CMIP6, recently we participate CMIP6 model, CMIP6 experiments with ICP scheme. You see the eastward propagation of MGO is quite close to the observation, especially over the maritime continent regions. Models show quite strong signal to this propagation events. And we also evaluate the extreme precipitation over land using the station data set. If you look at this recent publications, we check the extreme precipitation over land and compare with the CMIP5 models. And this is station part. That means the model did a pretty good job to capture the extreme precipitation over land, and this is this is extreme from the model. This is from the other CMIP5 models. The up panel is from your analysis, and this is some satellite product. Another extreme event is diurnal cycles. M panel is from GPM hourly satellite data set. We see a lot of strong diurnal cycle. The middle panel is from our 1 degree model, and the lower panel is from our quarter degree model. It's clear to see that even in middle low cost resolution model, the diurnal cycle of precipitation is quite close to observations, but the amplitude or extreme part is not as good as a higher resolution model. If you look at the monsoon region, both low resolution and high resolution show quite strong signal over the land. So at the middle night peak of the diurnal cycle from both low resolution and high resolution shows same kind of signal compared with the GPM satellite data. Okay, another extreme part is tropical cyclone. So you look at our 1 degree model and quarter degree model show quite similar signal to the IB track. If you look at the other 1 degree models, it cannot give quite reasonable tropical cyclone. This means our scale wheel convection scheme work quite well. And we also check the duration of tropical cyclone, especially over the West Pacific and North Indian Ocean. From observations, usually the tropical cyclone extends up to 8 days. For quarter degree model, we have almost 8 days. For 1 degree model, we have 6-day duration. It's quite comparable to observation. Over the Indian Ocean, both low resolution and high resolution are quite comparable with the IB track observation data. With this kind of model, we are set up a seamless prediction system. We call it FGOS F2 version 1.3. And this model, we use only 1 degree because we're trying to see computing results have more ensemble members. We have very simple initialization like nudging from atmosphere and ocean signal. We use time lag as ensemble approach. We have 4 ensemble members for reforecast, and the real-time forecast have 16 ensemble members. We cover 20-year reforecast, and we start reforecast frequency is daily. And this prediction we call S2D, or subseasonal decadal prediction system. In subseasonal part, we predict the following almost 2 months, and for decadal part, it's covered from 1 month to 10 years. And this operational system We call it green one because it saves a lot of electricity. We use only 16 nodes cluster HPC. We have a daily S2S, daily seasonal prediction with 2 ensemble members, and monthly we run the decadal part with 2 ensemble members. And then here we have a website to illustrate this result. I'm not going to the details, but this result also shared with some operational center, like they use our MJO for their operational purpose. And we also have the subseasonal tropical cyclone. Although we are only 1 degree model, but if you look at the daily result, you can see the tropical cyclone it clearly captured in this system. And we also predict the following 1 month and 2 months lead for the tropical cyclone frequency. And for the seasonal prediction part, just like regular seasonal prediction system, we predict El Nino and temperature or precipitation anomaly, and of course monsoon circulations. And we also predict the seasonal prediction of tropical cyclone. If you look at the recent publications, we evaluate models' performance in terms of seasonal prediction skill of tropical cyclones. Model quite good skill to capture the anomaly or variation of the tropical cyclone. We also check the real-time results during the recent 3 years, and the right panel you see that model did a very good job to capture the frequency, but as I showed in previous slides, the model failed to predict the intensity because it's only 1 degree model. That means the intensity is not good, but for the frequency is quite good. And we also submit our result to CI's prediction networks every year. This is the result from 2019. These results we not only predict for the average, we also submit the 2-dimensional CIs to SIPN, and the result is quite encouraging. In this year, our result is even better than MME. And this is the first decadal part. It's not only for operational purposes, also for research, because this is annual trend precipitation in the next 10 years. So we want to know where it can become drier, where it's become wetter. Okay, the 4th part, I'm going to report some application in Asia monsoon region. One of the most important application is S2S. We submit results to S2S project, and if you look at the news announcement from S2S project in last month, February 4th, exactly same day as Beijing Winter Olympic Games, the 20-year reforecast dataset has added to S2S dataset, and from last year we are keep to share or send our real-time prediction. If anyone wants to look at the model results or this prediction, you can go to the S2S databank and download the results. And the advantage also, the good is that the summation of our model results is quite timely. I download this plot from the S2S website. You see our summation is quite earlier than the other prediction system. Another important thing is the scale. If we talk about S2S prediction, we have to report what is performance of MJO. It's very important. Like this is like a El Nino in seasonal prediction part. from research paper, you can see that the previous prediction usually have about 23 or 24 days for MJO, but European Center did a very good job. It's up to 30-day prediction skill. We also check our submission to S2S during the last to check the data for the reforecast, 20-year forecast. The prediction skill from the full ensemble members, full reforecast ensemble member about 24 to 25 days. And this is the rho mean square error of RMME1 and RMME4, 2. And we also check the ensemble methods because we noticed that the European Center used 12 ensemble member. We only have 4 ensemble member, but we use time lag method to include more members from previous days, and the prediction skill is up to it's increasing to 27 days in the reforecast results. That means the more ensemble member can enhance the prediction skill MJO. And we also check the individual case from this return analysis. You can see clearly that individual case for control runs, the MJO for European Center is up to 20 or 21. We check our individual ensemble members at prediction scale of MJO is about 18 days. That means we still have a lot of space to improve the individual members of MJO in terms of MJO predictions. Okay. Another is we are trying to use not only for research purpose, but we also share to some Asian countries. Like this prediction system is help or support for tank fire in Sri Lanka. So if you still remember, in 2020 there is tank got fire, but we share our predictions, especially for tropical cyclone. We predict after 2 weeks there is tropical cyclone cross from South China Sea move westly to reach Gulf of Bengal regions.
Kindly wrap up. Kindly wrap up. This time.
Okay. Here there is a lot. We also share our report the El Nino predictions for China multi-model ensemble methods, and this prediction in terms of seasonal time scale is good to predict weak CP El Nino events. I wrote a paper to document this prediction. Also, the model predicts quite good for Nepal winter drought, and we also make summer outlook for precipitation in China. Due to time limit, I'm not going to detail, just give quick look at the future deflection. We are trying to use a stretched model to have the downscaling up to kilometer to trying to have more detailed prediction from both subseason or even longer time scale. Thank you very much.
Thank you, Dr. Bao. Is there any question on the chat box? No, I don't find. It's a very interesting talk on the developments up to the sub-seasonal to decadal. Any questions from the audience? If there is no question, let us thank Professor Bao for his very interesting talk on the sub-seasonal to decadal prediction in their goals. Now I request the next speaker, distinguished speaker, Dr. Shigeo Yoden. I saw him. Yeah, hello. Hello. I hope.
Thank you very
Yeah.
much.
So, Professor Shigeo Yoden and Vice Director of Institute for Liberal Arts and Sciences of Kyoto University. He had been the Professor of Meteorology of Kyoto University from 2002 to 2022. His major area research education are atmospheric dynamics, geophysical fluid dynamics, and climate dynamics. He won the 1992 Award Meteorological Society of Japan for the study on general circulation of atmosphere and team leader of the stratosphere, troposphere dynamical coupling in SPARG, SSG from 2005 to 2000, so many awards on tropical convective system from 2016. And he has also served as the president of the IUGG, IAMS International Commission on the Middle Atmosphere from 2007 to 2011. He will speak on the modeling monsoon process, especially by the use of equatorial quasi-biennial oscillation. Professor Yoden, please. I know that 15 minutes, we have time limits. So 15 minutes you will present and a couple of minutes will be there for question and answer. Thank you, Professor Yoden. Please continue.
Thank you very
Your
much.
slides are visible.
Professor Dash, thank you very much. Kind introduction. And can you see my slides or?
Yeah, you can, but yeah, it may not be the full screen.
Okay. How about this?
Yeah. Okay.
Pointer.
Please
Okay.
continue. It's
Thank you
visible.
very much. And I'm sorry, this is not the talk of the numerical modeling studies, but it's a free data analysis. But I hope this could be a interesting subject for numerical modelers for the motivation of a new test bed of the possible influence of the equatorial stratosphere, particularly the equatorial QBO, on the tropical convection system and their organizations. So I don't need to explain the monsoon itself. Yeah, this is a monsoon symposium workshop. But I think that this Shipichan's illustrations are a very good way to overview the monsoon systems. This is just a composite difference of the DJF minus June, July, August stream precipitation, and you can see the seasonal difference and importance of land ocean contrast. And my main subject, main interesting is the stratosphere tropospheric dynamic coupling. And these years I focused in the coupling in the tropics. And we started some years ago, SATIO TCS. It stands Stratospheric and Tropospheric Influence on Tropical Convective Systems. And last year, we published a review paper in Journal of Meteorological Society of Japan entitled Influence of the Stratosphere on the Tropical Troposphere. And this is one of the important illustrations, and this describes the three pathways of the QBO influence to the troposphere. And today's subject is the vertical downward tropospheric influence. But at the same time, there are two other pathways through the subtropical jet, and also the Horton-Tan relationship stratospheric pathway and northern annular mode to possibly influence the tropospheric weather and climate. And recently, we published a review paper on the influence of QBO on the specific MJO. And this is also the illustration and two panels, QBO easterly phase and also QBO westerly phase. And there is a systematic change of the temperature and the height of the tropopause and also the static stability. In the eastern phase of the QBO, called the higher tropopause and reduced stratification. And that influences the dynamics of the Madden-Julian oscillation. So eastern phase of QBO increase the Madden-Julian oscillation strength and activity, and propagation speed is slower, and increase the MJO predictability. And you can see this review that includes over 100 references for these 5 years or so, and you can use this linkage with to see the whole the paper. I'm sorry.
अरे सुनो तुम क्या है ना
So this is a
Yeah.
summary of the target. In the tropical troposphere, there are multi-scale interactions, the moisture convection, and they are intraseasonal to interannual variations. And there are two clear periodic forcing and response diurnal variation, and also annual variation we call monsoon here. And it's a large societal. I'm sorry, yeah, it freeze. Impacts in multiple time scales. And there is a stratospheric component to modulate, possible modulation of these variations. And MJO is this kind of interactions in the troposphere, but Son et al. Introduced the modulation of this by QBO. This is a new aspect of the stratosphere-troposphere coupling. And today's talk is this application is the modulation of the monsoon by the QBO. And yeah, we analyze only the neutral length period, and we separate boreal summer and austral summer. And we use precipitation data and also the circulation fields and 40 years data. And this is the zonal wind, zonal wind anomaly for the analysis period. And you can see the very clear signal in the QBO in the lower part of the stratosphere. And here's the monsoon chromatology. And the first slide shows the Gpcp precipitation and horizontal wind at 850 hectopascal all year at the top. And second is the June, July, August, DJF. And the bottom one is the difference between the two seasons. And these columns, the zonal wind and precipitation. And if we look at the difference, you can see the very anti-symmetric profile in zonal wind field of the U wind and precipitation, and symmetric for the W wind. And this is the real horizontal distributions, asymmetry. Similarly, yeah, we can see such kind of parameter composite difference between two seasons in OLR, specific humidity, similar to the precipitations, and also the mean sea level pressure, SST, horizontal wind divergence near the surface, and vertical motion in mid-tropos. And we can see a similar monsoon patterns, but individual quantities show specific features. Particularly, for example, the divergence field, you can see a very contrast distributions relative to other fields, and also the north-south contrast. Okay. So that's the background, and this is the main subject of the equatorial QBO and its influence. And we made a UFO analysis, and over 95% are explained by the first two components along the equator. So in the lower stratosphere, 70 to 10 hectopascal. And this is a phase plot of the PC1, PC2 space. And there are three colors, and black dot shows the neutral years. So we also use this. And we divide 8 phases. So for each 45 degrees, phase 1, 2, 3 through 8. And this is a particle profile, the zonal wind for 8 phases. 1 through 4 is red, and 5 through 8. And the dashed line is the composite difference with the opposite phase. So you can see the downward progression of the phase, and particularly we focus on the phase 4 and 8, and the largest difference at 50 hectopascal, and also the significant difference even in the troposphere, although the difference is very small, but statistically significant. I'm sorry. I'm sorry. Freeze. Okay. I'm sorry. So this is the composite difference between the opposite QBO phase. This is the difference between westerly phase at 50 hectopascal minus easterly phase, phase 4 minus phase 8. Precipitation, mean sea level pressure, wind, OLR, W wind, specific humidity, and hatched areas are significant areas. And these rectangular show the significant areas, and these are superposition. And this particular phase in Boreal some they are significant in the mostly in the along the equator, and also the northern and the southern hemispheres around here. And this is the composite difference along the equator, and here's the climatology in this longitudes, and you can see the climatologically Walker circulation, but around there we have a significant composite difference, intensification the Walker circulation, much wetter atmosphere, and enhanced precipitation or reduced precipitation in phase 8. And that constitutes the significant OLR around here, mostly I think over the maritime continent to Papua New Guinea. And this is a subtropical influence around Japan in the same boreal summer, June, July, August. And this is a climatology, and this is not the composite difference, but the phase 4 composite in the middle and phase 8 in the right. And you can see the intensification of Bonnie High in phase 8 and intensification of the circulations. And there is a dipole of the drier air, this area, and wetter is the western part of Japan. So a kind of a seesaw pattern, the altitude change in the seesaw patterns. And this is directly related to the difference in the tropics and also around the Philippines seesaw patterns. On the other hand, in the austral summer, DJF, we don't have much significant response along the equator, but mid-latitude, both northern and southern hemisphere. And the most important or interestingly is the Atlantic Ocean with much strong signals. And so again, this is climatology of precipitation and mean sea level pressure and horizontal wind. And you can see this kind of stationary Rossby patterns or cyclonic features in climatology in the northern winter, DJF. But phase 8, there is an intensification and the elongation of the strong wind regions. And you can see the contrast. And also there's a modulation or influence of the precipitations. And here's the dipoles. If you compare to the phase 4 and the phase A, there's an increase of the precipitation around this and a decrease of the precipitation here. And these kind of features are associated with the circulation patterns. And I think there are some other examples with a different phase of the QBO. This is a different phase 1 minus phase 5 and boreal summer. And again, here along the equator. And also this phase, there is a significant difference around the Indian monsoon regions. Okay. And this is opposite, austral summer between the phase 1 minus phase 8. And you can see other locations. And I'll stop here to show the detailed result of the analysis. And here's my summary of my talk. And by using global data of 40 years, climatology global systems are summarized, specifically for the neutral ENSO period, excluding the influence of El Nino or La Nina, and clear signals the zonal symmetric component and also the non-zonal asymmetric component with the contrast between the two hemispheres. And we introduced 8 QBO phases by the UF analysis of the deseasonal zonal mid-zonal wind in the lower stratosphere. And we applied the student t-test to show the statistical significance of the difference. Even though, 40 years not so long, so there are some limitations with the sample size in the same phase and season, in some of the phase of season. And QBO modulation of global monsoon system is investigated, specifically for boreal summer, June, July, August, and also the austral summer, DJF, separately. And we showed precipitation is a proxy, and also circulation phase. All of these are consistent and significant composite difference, particularly between the QBO phase 4 and phase 8. And this is characterized with the lower zonal wind at 50 hectopascal for each. And also the another phase 1 minus phase 5. And interesting in the several pathways, as pointed Haynes et al. We gave example of the equatorial pathway in associated with the weakening of the Walker circulation and the reduction of the precipitation over the Western Maritime continent, particularly in phase 8 compared to the phase 4. Subsequent pathways, we can give an example of the intensification of the western side of Ogasawara High around Japan and modulation of the pressure system and also the precipitation dipoles over the western part of Japan. And the opposite season, boreal winter DJF, we have a significant.
Hello, question
Okay, over the North Atlantic. So I think that there is a wide variety of internet coverage to be confirmed. Okay, thank you very much. This is all. Okay, thank you.
Thank you, Professor Yoden.
Yeah.
Thank you for a very, very detailed analysis of these 8 phases of QBO with the Indian monsoon. Thank you so much. Very
thank
interesting.
You very much. I hope some information for the modelers.
Yeah, there are several questions in mind, but you know the constraints of time, and we have realized that by presenting in limited time. Thank you so much. I don't find any this presentation is open for questions and discussions, but I don't find anything on the chat box. Anybody wants to raise at least 1 point? Okay, yeah. Takayu. Yukari Takayabu. Please.
Thank you very much
Very quick.
for very interesting presentation. I have one question. And why the equatorial difference is found only in the boreal summer, but not in the austral summer?
I'm sorry. This is a totally statistical analysis, and weak point is interpretation, particularly the dynamical interpretations. Yes. There is a large seasonal or month-to-month variations, and also the phase of the QBO. So I'm sorry, currently I have no answer.
Okay, thank you very much.
Thank you.
Okay. Let us thank Professor Yoden, and we'll quickly go to the next speaker, Professor Yuhei Takaya.
Okay, thank you very much.
So I would like to shorten his introduction. He has personally requested me so that you'll get adequate time. You can read, he is the editor of Scientific Editor Letters, Solar, and is senior researcher in Meteorological Research Institute, Japan Meteorological Agency. Professor Takaya, please. I don't want to take more time on this. Please start your sharing your slides.
I'm sharing my slides. Do you see my screen okay?
Yeah.
Hear me
you can
okay?
see. Yeah.
Okay. Good day, everyone. I'm Yuhei Takaya with Meteorological Research Institute. I'm honored to give a presentation on the subseasonal to seasonal prediction of the Asian summer monsoon. And in this talk, I update the current status and discuss the future direction. So after the short introduction of the data archives for the subseasonal to seasonal studies to facilitate the S2S prediction study, I present some results of the evaluation of the performance of the S2S prediction systems, and focusing on the dominant drivers for the Asian summer monsoon variability and the representation of their responses in the models. And I will discuss the future challenges and give a summary. So, so nowadays, a lot of efforts, we have several data archives for the S2S prediction studies. For seasonal prediction, we have the WWRP, WCRP, Subseasonal to Seasonal Prediction Project, S2S archive. We heard about this, and which includes the 12 models. And in addition, we have subseasonal experiment, the SubX database archives, which include the 7 models from the North American modeling centers. And for the seasonal predictions, we have several archives as well. And the WCRP Climate System Historical Forecast Project, CHFP, and the North American Multimodal Ensemble, NMME. In addition, there is Copernicus Climate Change Services, C3S, which is, they are all available for, really available. So in this talk, I will present some evaluation results. This is a part of our work in the WIGSHIP initiative. This slide just shows the precipitation climatology in summer in seasonal prediction models. On the right, we see the CHFP models, and on the left, we see the CHFP, and on the right, we see the C3S. And here I'm showing the Gpcp observations. And the models roughly reasonably capture the observed climatology, but of course we know that the model always have the biases. Here, to illustrate the biases, I'm showing the C3S multimodal ensemble the precipitation biases of the C3S against the Gpcp observations. And we see the excessive rainfall bias over the tropical western North Pacific and North Indian Ocean, and deficient rainfall bias around the coastal East Asia and South Asia. And these biases are persistent. We know that there is persistent biases, and these biases, the CS3S model and the CMIP models share these kind of bias. But we see some progress in the past. Here I'm showing the pattern creation of precipitation climatology in summer over the Asian summer monsoon region, the box here. And basically, this slide shows the latest models. The C3S models have higher pattern correlations of the precipitation compared with the models, the older models in CHFP. And almost all of the models have, C3S models have the higher pattern correlations than the median of the correlation of the CHFP models. And this is good. But the participating models institutes are different from CHFP and C3S. So I extracted the models of the same institute. Here I'm showing the Met France, JMA, ECMWF, UK Met Office, and NOAA in the C3S and CHFP. Again, we confirm that we see a decade of progress in terms of the representation of the precipitation climatology. And the pattern creation of the climatological precipitation over the Asian summer monsoon region exceeds 0.8 in some models. So we are happy with these results. And this slide shows the pointwise temporal correlation scale for JJA precipitation. In this kind of exercise, dependence of the skill scores on ensemble size makes it difficult to compare the skill of the different systems. So here I'm showing the estimated correlation skill of infinite member ensemble following the Murphy 1988. So we can compare the skills. I'm showing the skill of the multimodal ensemble of C3S, and the patterns are consistent with each other. And again, this slide shows the area averages of temporal correlations for JJA precipitation over the Asian summer monsoon region. And again, we see a decade of progress, and almost all of the C3S models on the right have the higher average correlation than the median of the CHFP models. And this is the similar plot as I showed before. And we see a decade of progress in terms of predicting the interannual variability of JJ precipitation in C3S and CHFP. And I know that there have been a lot of efforts to achieve this this improvement. So I would like to congratulate those who contribute to the model development. And we can clearly see the progress in the last decades, because the C3S is the latest system, and the CHFP has the models decade ago. So the next question is where we can predict, or where the predictable regions of JJ precipitation. What I'm showing here is the number of models that have expected correlation skills exceeds 0.3. And in the CHFP and C3S model. And we can identify the potentially predictable regions. For example, tropical western North Pacific, maritime continent, Arabian Sea, eastern and western Indian Ocean, and Ganges region, south part of the Indian subcontinent, and central China to Japan and Mayu region, and coastal region of Indonesia. And we see the consistent results in the CHFP and C3S, so we expect the skillful prediction over these regions. So let's move on to the dominant drivers for the agent summer monsoon variability. This is just showing the dominant climate drivers for the subseason to season predictions. The S2S predictability arises from multiple sources, including the MJO or IOD, Equino, and so on, Indian Western Pacific Ocean capacity model. So this slide shows the dominant coherent variability of the agent summer monsoon. Namely, I computed the singular value decomposition analysis for SST and precipitation over these regions. And I'm showing here the heterogeneous correlation maps of the SVD analysis for SST and precipitation. The colors indicate the precipitation correlation of the precipitation, and contours indicate the SST. The first mode represents the nth mode with the warm positive anomalies over here, and the active convection here, and then suppressed convection here. And the second mode represents the Indian Western Pacific Ocean capacity mode, which features the warm SST conditions over the Indian Ocean and South China Sea, and the active convection over the Indian Ocean, and the suppressed convection over the tropical Western Pacific. And these two dominant modes actually drives the regional variability. On the right, I'm showing the SVD analysis for summer precipitation and SST from the Mishra et al. And they found that the nth mode and IPOC mode actually drive the regional precipitation over the India. The first mode represents the positive dry conditions when we have the El Nino, and we see dipole pattern. And we can see the similar features in the SVD analysis I showed in the previous slide. The dry conditions with the nth condition and the dipole patterns with the IPOC mode. So representing these models is important. And these signals are related to the predictable regions. Again, we see strong signals of the nth mode and IPOC mode over the predictable regions we identified. So representing these modes are important for improving the seasonal prediction model. And this slide shows the representation of the nth mode in the C3S models. I can go in details, but basically almost all latest models capture overall nth influence on the large-scale precipitation. But if we looked at the regional pattern, some, not all, reasonably capture regional precipitation over the South Asia. And this is the IPOC mode. This slide shows the IPOC mode. We can see that the representing IPOC mode seems to be more difficult than the nth mode, but the majority of the models roughly capture the observed pattern. And we can see that some models present the IPOC mode, IPOC-like patterns. So how this representation of the climatology or the teleconnection relates to the prediction skills? Here I'm showing the precipitation prediction skill with respect to the pattern creation of precipitation climatology over the Asian summer monsoon region. And we see a good relationship between the precipitation prediction skill and the pattern creation of precipitation climatology. See. But if we looked at the C3S models, more plots are a bit scattered, and what do make the skill difference? So I checked the representation of teleconnection, and on the left we see the precipitation prediction skill with respect to the centered pattern creation of NIN 3.4 SST teleconnection. Here I computed the uncentered pattern creations of the regressed precipitation pattern on the NIN 3.4 SST. And we see positive correlations. So this means the improving the representation of the ENSO rainfall teleconnection is a key for improving the seasonal prediction of the rainfall. And on the right, I'm showing this similar plot for the IOB or IPOC mode teleconnection. And if we looked at the C3S models, we see a positive correlation, but we don't see a clear relationship for the CHFP, because some models actually have the not good representation of the ENSO teleconnection. So, but for the C3S model, we see a good relationship. So let's move on to the subseasonal prediction. Oh,
Kindly wrap up.
yeah, okay. This slide is just showing the example of the subseasonal predictions. Now S2S focus are now reality, and however, if we looked at the handicap skill, the skill is still low, which emphasizes the needs of the future improvement. But there is hope. We know that the boreal summer interseasonal oscillation is key for the subseasonal prediction. The previous study evaluated the skill, and the ECMWF model presents steady progress in predicting the precipitation skill over the India, and we see a steady progress improvement in terms of the BSI. So future challenges, we need to improve the skill. To do that, we need more process-based understanding of the model errors. We anticipate the user-oriented focused information, including the monsoon onset for agriculture. So I'm conscious of time. I just stop here and leave the summary. Thank you for your kind attention.
Thank you, Professor Takaya. Thank you very much. Is there any question or quick point to discuss about? If not, I don't find it. There's no raised hands also. Thank you so much to speak about this S2S core project and very interesting ideas. Now we are really very much constrained with the time, and we have already run out of time. So I don't want to speak much on this issue of what were being presented. You have had all the presentations, and we had a couple of discussions. We could not have discussion on one or two presentations. I now thank all the presenters and also the speakers who wanted to ask some questions. They can contact them, the speakers, privately to get their clarifications on this interesting work done by all the four scientists. Thank you so much.
Professor Das sir, for nice chairing the session, and we had very good 4 talks. And thanks to you, chair, and as well as all the speakers. for very excellent talk. Actually, it is available. So there are not much time for question and answer, but anyway, we can write to the speaker directly. The video will be available. YouTube is available, so yeah, that can be there. Thank you, sir. Thank you very much for the sessions. So yeah, this hall again we will continue the parallel session. So that just in 2 or 3 minutes we are going to start that one. Hall B already people have joined. So here hall A we will start in just 2-3 minutes. Let me see who are the people available, the speaker, the parallel sessions. The Dr. Dev Niyogi, is it available? He has to coordinate the session, but if he not available, so we will do that from our end. Okay, so not that. Then about the party speakers, yes, Sipra Jain is available.
She has given the recorded video.
Oh, she has given the recorded video. Okay, so that means that video you will play from our side now. Fine.
Yes, sir. And she will be available online also to give any comments or to give reply for the questions.
Okay, she will be available online.
Yeah, that's what she communicated.
Okay, so recorded video available. Then what about next second talk, Ankur Gupta?
Yes, sir, he is available.
Fine.
I am available.
Yeah, Shiromani Jayavardhane. I think we have moved this talk. I think.
Yeah, I think he sent a video message, and he's probably happy to join after my talk because he has some electrical power cut problem. So if that's okay.
Okay, so say sir, after
yeah,
your
it's
talk, you'll join.
yeah, I'm there. Yeah.
Karuna Sagar? No.
Karuna Sagar, no, sir.
Yeah, okay. Then last one, that Periel Philippe, there?
Yes, I'm here.
Okay. So yes, so let us start the session. First, the climate change and monsoon by Siprajan. So we have got a video, recorded video. So I will request our team to kindly play this.
Hello, everyone. My name is Shibrajan, and I work as a project manager at the University of Edinburgh. I would soon be joining Center for Climate Research in Singapore, and that is why I cannot do this presentation live because I would be somewhere in transit. So today I'm going to talk about the extreme trends that are possible in Indian summer monsoon rainfall for multi-decadal timescale. In this work, we propose a methodology where we have used the seasonal hindcast for multiple seasonal prediction systems to provide changes in Indian summer monsoon rainfall that extends up to like 30 years in future. Since the time is limited, I'm not going to go too much deep into the methodology, but I wanted to give you a little bit idea of what we did. So I'm using the seasonal hindcast data, the rainfall hindcast for June, July, August mean, which were initialized with May start dates from the Climate System Historical Forecast Project. Before using the models that are available through this project, we have carried out some fidelity tests for mean climate. We have looked at the biases and bias corrected the rainfall hindcast using the climatological difference between ensemble mean rainfall as well as observations. We have looked at the various interannual variability correlations and made sure that the models that we select are skillful. We have also looked at the probability distributions, mean, standard deviation, skewness, and kurtosis, as well as the ENSO teleconnections to ensure that the teleconnections that are simulated in these seasonal prediction systems are comparable with the observations. So the fidelity test summary on more details are provided in 2 of my papers, which are provided on this slide. So the idea here is to sample a large range of internal variability and study the plausible changes in the extreme rainfall and quantify the risk of those extreme trends. So we arrange the data in the format that I show in the figure. There are 69 ensemble members in 33 years. I want to emphasize that it's really important to preserve the order of year because we want to preserve the climate signal in the rainfall hindcast. So for each calendar year, I selected 1 ensemble member randomly by bootstrapping and created a resample time series. And this was done for each length starting from 10 years to 30 years. And for each length, I created 10,000 time series. So now using these 10,000 time series, I have answered a series of questions, which I'm going to show you in my next slide. But before we do that, I wanted to give you a spoiler of the key result of this methodology. So the graph that you see here shows the changes in rainfall for the next decades using CMIP6 and CMIP5 projections. And one of the time series that you see here is a pseudo time series or the pseudo projection that I am giving using the hindcast data. So what I wanted to do is pick one line, make a wild guess which one it could be. And towards the end of my presentation, I'm going to tell you that which one out of these all projections is from the seasonal hindcast. So the first question that we are trying to answer that why there are trends, the wetting trends are missing in observations. As you may already be aware, for the late 20th century, starting about like 1950 to up to like 2010, the observations showed a really strong drying trend, particularly over the north central India, whereas the generations of the CMIP models have been showing a consistent increase in the Indian summer monsoon rainfall. This has been really puzzling, that why there is a mismatch between what models have been projecting and what the observations show. And to explain this mismatch, various hypotheses have been proposed. For example, changes in aerosol loading and forcing warming of the Indian Ocean, or changes in land use and land cover. Here, we emphasize that these drying trends can also occur by chance, and that is the null hypothesis that I'm testing here. The figure that you see shows the probability distribution of the rainfall from the CHFB and the observations. And as you can see, the observations lie well within the envelope of the internal variability that is sampled by the multimodals here. In fact, we found that the internal variability can be large enough to negate or even overwhelm the wetting trends due to the greenhouse gas forcing into the climate and give a temporary drying trends. There is another interesting result that we see in this figure. If we go from the 10-year to 30 years, the PDFs are consistently shifted towards right. That means that wetting trends are being more favored over drying with the increasing length of the period. I think that it has a lot of implications from a policy-making perspective. So, for example, if we are looking at the 10 years in future, then flood and drought could be equal risk because there is an equal chance of wetting as well as drying. But if you're looking out to like 30 years or even longer, then floods are definitely a higher risk. So our resources as well as policies, I think, should be inclined towards tackling the floods. So the second question that we're trying to answer, what are the chances of wetting trends as compared to the drying trends? So for a 10-year period, there is 60% chances of getting a wetting trend, whereas the chance of getting a drying trend is 40%. But as we go towards the longer period, to 20 or 30 years, the wetting trend chance increases to 70 and 80% respectively. We have also compared the worst possible event from the observations and the multimodal ensemble. And as you can see, for all the periods like 10-year, 20 or 30-year, the observations under predicts the chance of worst possible as well as the magnitude of worst possible event. So our key conclusions from this graph is that the observations underestimates the intensity of worst case scenarios, and these intensities or these probabilities are more uncertain as we go towards the longer period, and it's purely because the observational data is available for only 100-year period or so over the Indian summer months, over the Indian monsoon region. So here is the graph again that I showed you in the beginning. Here we compare the predicted change in seasonal hindcast with the CMIP6 as well as CMIP5 projections. The solid line that you see in this graph shows the mean change, and the CMIP projections shows that for high as well as medium to high emission scenarios, Indian summer monsoon rainfall can change by about like 2 to 6% by the year 2050. And we got a similar estimate from the CHFP, which shows about like 5%. So we think that it's within the range which is projected by the CMIP. We are also looked at when can we expect the climate change signal to emerge outside the envelope of internal variability. So the dotted red region that you see here shows the envelope of internal variability, which I have created using the 10,000 time series of each year. So the shaded region shows the 1 sigma deviation. And as you can see in this figure, all the solid lines for all emission scenarios lie well within this shaded region, and therefore we do not expect the climate change signal to emerge outside the envelope of internal variability, at least until 2050. We have looked at the impact of trends in sea surface temperature, the figure that you're seeing on right. Here I've compared the trends in rainfall with the trends in sea surface temperature for the length 20 years. The correlation is relatively low. It's for about like 0.2 to 0.3, but I want you to focus on the slope. So over the 20 years from the last figure, we estimated that climate change can lead to a mean change of 30 mm rainfall, and that's the increase in rainfall that we expect to see in the next 20 years. But from this globe, we can decipher that if there is a 1.5 degree cooling or heating of the Nino 3.4 region, it can actually double or negate the projected change in rainfall, and even even larger change of up to 80 mm over the 20 years is also possible. And we also found a similar sized but relatively lower impact from the East Indian Ocean, but relatively higher impact from the West Indian Ocean. So here I'm looking at the role of background circulations in driving extreme changes. So we looked at the time series which gave us the most extreme trends out of the 10,000 time series, and we found that there were several instances of the extreme wet and dry JJA summer monsoon precipitation during the most extreme trends. So from our multi-model ensemble, we took 10 wettest as well as 10 driest ensemble members and years, and we looked at the upper level, that's the 200 hectopascal wind anomalies. As you can see, there is a really nice circumglobal Rossby wave that's traveling across the globe, and it appears that it's emanating from the North Atlantic region for this case. The tinted region here shows the region for which the Rossby wave propagation is not permitted according to the Zoonomy theory. But as you can see, the Rossby waves is very well contained in the waveguide that we have plotted here. So we expect that the future changes in the rainfall, at least, and specifically for the longer periods, would be strongly affected by the intensity as well as the propagation of these waves. So here are some key takeaways from my talk. We found that the wetting trends are systematically more favored over drying, but the drying trends can occur in the observational record just due to the internal variability. And we found that the past changes in the rainfall, particularly the drying changes, can also be explained by the internal variability, as it's large enough to revert the wetting trend in rainfall due to the greenhouse gas forcings. The largest 10-year trends that we see in current observational records show about like 20% reduction in JJA total rainfall. But from the multimodal ensemble, we find that this reduction could even exceed 30%. So the chance of occurring that would be relatively lower. We also calculated the 1% probability values, and we found that for any 10-year period in the future, there's a 1% chance that the monsoon rainfall can increase or reduce by 1/5, almost like 20% over the next decades. We found that the observations give a poor estimate of the most extreme trends, particularly for the periods which are longer than 10 years, whereas the multimodal ensemble obviously gives a more statistically robust estimate. The climate change signal is not likely to emerge outside the envelope of internal variability by the year 2050, and the trends in the rainfall are strongly impacted by the trends in the sea surface temperatures over the Western and Indian Ocean, and 1.5-degree warming or cooling of these regions can double or negate the influence of climate change on rainfall trends. So in addition, the circumglobal Rossby wave trends is a potential avenue of future research for the decadal prediction of Indian summer monsoon rainfall. And with this, I think that I can end my presentation. If you have any questions or feedback, or if you just want to catch up for a casual discussion, please feel free to email me at this email ID. This is my Gmail ID, as my official email ID is not active yet, but I check this inbox quite frequently. So thank you so much for listening to me, and I hope to hear back from some of you. Thank you so much.
Thank you very much, Dr. Sipraji, for a nice video. Actually, yes, it's very interesting talk. Definitely people will contact you for further information or for further query. Thank you very much. Now we'll move to the next talk by Ankur Gupta on subseasonal to seasonal prediction system at Ensembles Lab, rainfall predictivity and associated teleconnection.
Yeah, just a minute. I'm just sharing my screen. So, are you able to see my screen?
Yes, we can see.
Okay. Hello, everyone. So, my talk is on the subseasonal to seasonal prediction system at NCMR WF. Basically, I'll introduce. I'm not able to move my slide. Okay, now. So here I am briefly describing the system we have at NCMR We have both the systems at S2S time scales are based on a couple model in which the atmosphere is at 60 kilometer. We are using a version of unified model. It's coupled to the 25 kilometer ocean model, NEMO in this case, having a 75 levels in the vertical. So for both, to support the forecast, we carried out a set of hindcasts, which is 23 years long from 1993 to 2015, and and the extended range prediction system is based on a multi-week forecast, so up to 4 weeks of forecast. So every week from Sunday to Wednesday, using those initial conditions, we issue we carry out 4 runs up to 36 days of simulation. So that makes like 4 members per day and 4 days in a week, so 16 members. And to be compatible with the IMD's definition of the week, we issue a forecast on Thursday for the week beginning on Friday to next Wednesday. So here I am showing some of the sample forecasts which were issued in the last 1 year in 2021. So in the right we can see an active a forecast verification for active phase and a break phase In this case, the active phase was in 9th to 15th of July, which is shown in the observed plot for over the extreme left, and then corresponding to the 4 weeks of lead times of forecast valid for the same time period. So we can see in the 4th week forecast also the model is able to capture the spatial structure very well and the intensity of the rainfall. Similarly, for a break phase from 25th of June to 1st of July, we can see that the model is able to capture the spatial pattern of the rainfall, of reduced rainfall in the northern regions, Indo-Gangetic plains and eastern in India in week 4 also. Coming to the seasonal forecast, this is the kind of forecast we kind of plots and the forecast products we make for the seasonal forecast. So for 2021, the bottom panel, the first row is showing the full fields of forecast, then the anomalies, and then the probabilistic forecast. So we can see for 2021, the forecast was mostly in the normal category for most of the grid points, except in some of the areas it was above normal. We have also started looking into the snow forecast, which is important during the season of December to February, and we see that the model do have a lot of interannual variability, but we are in the process of comparing it with the observations here. So we are not issuing the snow forecast yet, but we are just looking into these kind of products as well. So here I'm showing the skill of the system across the time scales. So towards the left, we have this is the weekly skill over the Met subdivision. So in the four plots are for different lead times, week 1 to week 4. And in the week 1, we can see the most of the skill is above 0.5. In week 2, most of the subdivisions, Met subdivisions have skill above 0.4. So, but in week 3 and week 4, we barely see any useful skill. So, so remembering the previous plot in which I have shown some of the forecast is good in week 4, but when we are looking at the skill over a longer time period, we can say that we can rely on this system up to for the week 2 forecast only. So in the center panel, I have shown the monthly skill at different lead times. So this is the lead times here is like 0 days, 5 days, 10 days, and 15 days, which I'm denoting here by painted leads. So suppose you for the next month one wants to issue a forecast on 25th of the month for the next month. So this kind of analysis can tell us that what kind of skill the model has at those time scales. So we can see for the Central India the skill is about 0.6 or 0.7 for up to at least 10 days actually of lead times. And then comparing across the different homogeneous regions, we can see that the Northeast has the lowest skill. And I have done some analysis which shows that this is because of the more spread in the model, and the noise in the model is more in the Northeast compared to the other regions. Similar information is shown on the right panel, except over the spatial plot over different homogeneous definition of different homogeneous regions. In this case, it's homogeneous region. Again, these are the first painted lead times for the monthly rainfall. We can see the very useful skill for the monthly rainfall over most of the regions of the India. This is a continuation of the skill analysis at seasonal time scales, and I'm comparing here two different systems. One is very close. One is UK Met Office, which is our own system is very close to the UK Met Office, and comparing it with the ECMWF seasonal forecast. So this is the interannual variability of JJS mean rainfall. We can see that both the models are able to capture the interannuality well. On the seasonal timescales, the skill is less, 0.5, but for let's say the model initialized in May. But we can see that if we talk about the sign of the rainfall, those are captured quite well by actually both the systems. So in this case, 11 out of 19 seasons, the model is able to capture the sign well. So this is our system is just slightly better than ECMWF, which is able to capture the 10 out of 19 times. But more importantly, I would like to highlight the years of failed forecasts, in which are common in both the models. So the droughts of 2002, 2009, and 2016 are not captured by either of the models. Similarly, the above normal rainfall of 2006 and 2013 are again not captured by the model. So these suggest the kind of signal is quite similar in both the models. For the seasonal prediction, we would like to look into how the drivers of the monsoons are captured well and what are their teleconnections with the monsoon of seasonal mean rainfall. So here I am showing the internal variability of Indian summer monsoon rainfall ISMR Nino 3.4 index, Equino, which is the equatorial wind index in the equatorial Indian Ocean, and the DMI, which is the SST difference in the anomalies of the SST in the east and the western parts of the equatorial Indian Ocean. So here we can see the internal variability is captured again well by the model. This is the model initialized in June for the JJS mean, and Nino, for the skill of the Nino is quite high, more than 0.9, but for ISMR it is 0.6. This is for model initialized in June, so the scale is slightly higher than what I have reported, what I was saying lastly for the May initialized model. But for Equino it is almost 0.4, and for IOD it is 0.5, so much less than the Nino, which is the main driver of the Indian summer monsoon. So looking at the observed teleconnections, the top panel is the observed teleconnection, the bottom one is the simulated teleconnections, again the JJS mean. So here we can see in the left the ISMR correlation with the Nino, in the center relation with the Equino, and in the right part the relationship with the combined index of Nino and Equino. So by incorporating the information of Equino, the variance explained by this combined index of the variability of ISMR has increased slightly. So this is a good sign of having more information from the observations into the predictability of the ISMR. But when we look at the simulated teleconnections, the Nino teleconnection is simulated okay, but although it is quite overestimated. However, the Equino teleconnection with ISMR is not at all represented by the model. So these are some of the areas where for the future model development, and from where we can expect to get more skill by improving these processes in the model. These are, I'll just skip these ones. I just want to stress out this. We got some data from IMD for the weekly forecast in 2018, and we just compared the performance of both the models. So although from 2018, just 1 year, it's not possible to compare the skills. So these are just a sample plot. Both the models are able to capture some of the signal by week 3 also. In this case, I'm showing the observations from 12th of July to 1st of August in 2018. So this is a case of northward propagation of rainfall. And you can see the third row, which is the NCMRWF model. It is able to capture that northward propagation in the week 3 also. And this is not a selected plot. I mean, any plot we will see the second week will look very good, and the third week sometimes it gets the signal, sometimes not. In this case, the IMD CFS was able to capture the progression up to week 2, but not in week 3. But if you look at some of the other biases, NCMRWF has, as you can see, the rainfall along the Arakan coast. That is not captured by the NCMRWF model, but while it is very much there in IMD CFS even in week 3. So this is to say that if this is the case for combining both those models for getting the extended range forecast, and IMD has already started doing the seasonal forecast at the multi-model level, so it may be useful to do it for the multi-week forecast. I just want to leave this with.
I think you can just summarize.
Yes, just one more minute. So this slide is actually representing some of the challenges we have in forecasting of rainfall during the JJS across the time scales, even the daily rainfall. But Beginning with the seasonal rainfall, I think this is the plot which everyone is familiar of working on the Indian monsoon, that we have a dry bias. So on the top right, top left, we can see the UKMO dry bias. Similar kind of bias is present in the ECMF, although it is slightly lower than what we have in our system. Towards the right, we can see the similar kind of information at the monthly time scale. So we can again see some drying of rainfall over the Indian landmass for different months. It's more in June, July, less in September, but it is there. Most importantly to note over here is I have shown the weekly biases for the week one. So how these are developing early in the model integration. So here we can see that the dry bias over the India it's starting with week one, and by week four it's already very much there and looking very similar to the seasonal biases. So these are some of the areas that if we improve the daily our medium range, it may have possibility of improving our seasonal forecast also, combining with this improving some of the teleconnections. So these are some of the conclusions. I'll not read them now, but some of these findings are presented in the papers listed here. Thank you, and I welcome any questions from the audience.
Yeah, Ankur, very nicely you have discussed about the sub-seasonal and seasonal model, and also is advantage is good to means how it is able to capture even week 3 also. Yeah, at any time we can combine it, and since lack of time we are not having any question also, so we'll discuss further on this matter. Okay, thank you, Ankur.
Thank you, sir.
Yeah, so we'll go down to the next speaker. It is Jayavardhane or Seshagiri Rao.
I can go ahead because I have school run as well. That would be great.
Okay,
Thank you.
Please go ahead.
Can I share my slides, or do you will share?
That depends on you. If you can do, fine. Otherwise,
I can do, I think. Share.
हाँ आशीष, अच्छा उसका बना पाओगे क्या?
It's not allowing me to share. Can you share, maybe someone?
Yeah.
Sir, did you upload your presentation?
Yes, I uploaded it. What do you mean? It's in the PDF format.
1 minute. Special distribution of convective elements used to quantify the degree of convective organization.
Okay, maybe I can. It's coming now. Can you see it?
Yeah.
Yes. I can see it.
Yes.
Okay, that's great. Thank you. Sorry for this technical issue. First of all, it's a great pleasure to talk in WMO-7 meeting conference. So this work is carried out under the WCCP India. So my name is Sheshagiri Rao Kolusu, aka Sheshu Kolusu. So I work at Met Office. And I also thank here my colleagues from NSMR-WF, from Ashish and Ashrit. So this is a good collaboration between the UK Met Office and NSMR-WF piece of work. So my talk is a novel comparison of ensemble precipitation forecast accuracy and skill for the 2019 Indian monsoon season. This is my content for the presentation. So what is the motivation of this study? Basically, we would like to understand the use of like short range and medium range models to inform for early preparedness and early warning for extreme or impactful weather events, for example. So we have in this study that's the goal of the study, and I have used two different forecast modeling system, one from Glossy 5 UK Met Office Global Ensemble Prediction, and another one from NSMR-WF NEPZ. They have two different time scales and spatial scales. Like we have, like Met Office model has a 60 kilometer, and then NEPZ has a 12 kilometer, and also it has a different vertical levels, and also type of perturbation is type of ensemble generation also different. Keeping in that mind, we would like to assess the skill of these two models for the 2019 monsoon season. So for this, we have used the GPM image rainfall data. So I'm talking only about the rainfall. And all the data sets are regraded to Glossy 5, which is a coarse resolution from the high resolution data tool. And in this study, I'm talking about the different performance metric like RMSE and mean biases and the actual and potential skills. So in order to estimate the skill of the volume of the precipitation, what we did basically, we adapted the Wheeler et al. Methodology, where he accumulated with the different lead windows and different lead accumulations. So for example, we take 1 day window, 1 day lead window, lead time, and with next 1 day accumulation. So 1D we call, and the second day lead time, and you accumulate another 2 days forecast, and so on. So you can go ahead up to from basically different time scales, weather time scales, so seasonal as well. But because of the length of the forecast, so we can only go up to 40, which is almost week 2 forecast to compare both the models. And this is the, from the global model to we choose the domain of Indian domain. This is our study region, and most of the people know India has a different homogeneous rainfall regions. So we also separate them. We also look into the different metrics at this subdivisional scale as well. So one of the study here, I'm showing the CRPS continuous rank predict probability score, and you can see the CRPS score is increasing with the lead windows, and this CRPS can be decomposed into two parts from based on the hash batch. One is the reliability part, one is the other resolution and uncertainty. So the reliability is basically these are the two models. You can see one would expect if both the models have a good reliability, they should be 0. So as you see, would you want, 1 day and 2 days lead time, the reliability, when the lead time is increasing, the reliability is reducing, and also the CRPS spot, uncertainty is also spreading more. This is the one of the how the model mean error is increasing with the different lagged ensembles. So this is from the Glossify model, UK Metaphysics model. We have a 40 members can generated by lagged because we have a forecast system for two ensembles each day at 2 different time scales. So by using that 4 members per each day, so we generated the 40 members. So overall, what you see, the error of the precipitation is increasing with the lead windows and with the lead lagged ensembles, for example. And you can see dry biases over the continent and wet biases in the ocean region. Whereas when you go to the NEPSG from the NCMWF model, the errors are different, but more or the similar patterns of error is noticed, that we have seen in the RMSE as well. So this is the RMSE over the core monsoon zone region from the Glossify model. This panel, upper panel, and this panel is the lower 2 panels of the NEPSG model. So NEPSG, you can see the errors are with higher lead windows. It's it's staggered, it's flat. But whereas in the Glossify, it is increasing trend. That's because of the lagged ensembles. One point to note that at lower lead time, Glossy 5 has a lower RMSE than NEPSG, for example. So these are the errors. We are trying to address the bias, correct these errors from some other study from my colleague Marian. She was unfortunately she was unable to present here. So the other performance metrics here I have shown you, which is the actual skill of the model from the Glossify and NEPSG. So these are the spatial patterns of NEPSG. Actual skill is basically the correlation between the time series of model and observation. The first column is the NEPSG spatial pattern. You can see the actual skill is increasing with the lead windows. The second column is the difference between the Glossy 5 and NEPSG skill. But you can see the pink dotted lines are we have done the SPCT kind of test where it gives the significant test of 90%. So overall, NEPSI has a good actual skill compared to the Glossy 5 over the season, and these are the again the latitudinal longitudinal latitudinal variation of the skill difference. So and the arrow shows the statistical significant test significance, which if they are statistically significant in the skill, that should the arrow should not fall into the zero line, but most of the arrows are following the error bars are following in the touching the zero line, but some of the you can see the pink one they are not touching. So there is some locations NEPSI has a, I would say strongly significant in improvement in the forecast compared to the Glossy 5. But however, overall, I don't think so they are statistically significant. This is again showing we also looked into the sensitivity of the ensembles. So from the two models, and again this is the different in x-axis you can see the different homogeneous regions, and y-axis is the difference between the actual skill in the first column. This is a potential skill. That's another metric. I'm not going to definitions of these potential skill and all because of lack of time. So what we see here, the full ensemble skill, first column, and the second one is if you reduce the only 23 members, what is the skill in the Glossify, because Glossify has a 40 members and NEPSI has a 23 members. So we try to reduce the world members from the Glossify and see if there any skill improvement. So over the central India, this is for full ensemble, 23 ensemble, 8 ensemble, and 4 ensemble between the both models, and the skill difference. They are quite central region at 1D, at least first lead time, they have a significant significance in the skill. The differences are better. For example, NEPSI is better compared to Glossy 5. That's only happening over the central India, not in the other regions. For example, the same as the potential skill, some locations and at different windows, lead windows, the skill is performing. So there is no clear signal from statistically there is a strong improvement in the NEPSI skill over this extreme monsoon season. And as I said, Marian is working on my colleague working on how do we correct the bias, these errors, by using their own forecast rather than using either observations or hindcast data, to get ready, set, and go to provide the forecast and for the decision makers, for example, to give the early warning for extreme weather events things. So yeah, this is my conclusions from my study. I would welcome to take any questions. Thank you. These are my collaborations. We thank to all the collaborations under the WCCP India. It's a great project to work. Thank you.
Thank you very much, Dr. Sheshu Kurosu. Yeah, for your nice talk, how you are doing the collaborative work with the NCR scientists, and also you have shown the bias correction. So this is a good thing that models are improving. And now, if there is any question, so let me see. Yeah, it is not there. If anybody has any question, directly can ask. Okay. So I think there is no question. So let us thank you, and we'll go for the next speaker. Yeah, you have joined us. Okay, very good. Over to you, ma'am.
Okay, thank you very much, and good morning, good afternoon, and good evening. Let me share my presentation from this side. I hope you can see my presentation now.
Yes, yes.
Okay. So I'm going to present a case study about subseasonal forecast for disaster risk reduction. May 2018 extreme rainfall event in Sri Lanka. I'm Shiromani Jayawardena from Department of Meteorology, Sri Lanka. My co-authors are Thierry Lefort, Meteor France, Sarat Premanal from AdDream, and Chatura Riyanage from Disaster Management Center, Sri Lanka. From 19th to 27th May 2018, we received heavy rainfall over northwestern, western, and southwestern parts of the country. Leading to severe flooding in northwestern and flooding and landslides in southwestern parts of the country. And especially on 20th and 22nd, more than 200 millimeter rainfall received over this part. And according to the Disaster Management Center, 175,000 people have been affected across 19 countries and 26 people killed. Worst affected districts are districts located in the western part of the country. So these are the synoptic scale analysis. So we can see like a trough to the east of Sri Lanka from 19th onward, and then this deep trough over east north-south direction, deep trough over Sri Lanka after 24th. And then this is at 850 millibar layer, and at 500 mid-levels, 500 millibar layer, we can see mild cyclonic circulation over Sri Lanka, especially 19th, then 20th, and again from 25th, 26th. Nearly 3 weeks before that, this event, I received an email from Thierry Lefort. Actually, he sent this email to the Monsoon group. I have subscribed to this Monsoon group. In that email, it mentioned that based on the ECMWF monthly forecasting system, a better defined MJO is likely to enter to the Indian Ocean by day 20. So this was on April 27. And based on our previous research, we found that when MJO entered into the phase 2 and 3, especially during southwest monsoon, as well as especially during month of May, extreme rainfall is likely to occur, especially over western part of as well as southwestern part. So this study has conducted based on data from 1981 to 2010 and using RMM index. And so this is the MJO composite of weekly rainfall probabilities exceeding 90th percentile. So we can see a higher possibility of receiving extreme rainfall over the western part and south as well as southwestern part in phase 2 and 3. So this is the actual RMM index from Bureau of Meteorology. So like ECMWF monthly forecast system predicted, so it entered to the phase 2 on 17th and then stagnated there till 27th, and then entered to the phase 3, 28 and 29, and then entered to the phase 4. Then when we analyze this ECMWF S2S ensemble prediction, we found that 4 weeks before, so this indicate wet signal over western part, then 3 weeks before again wet signal over most parts of the Sri Lanka, and again 2 weeks. So the consistency of this prediction as well as MJO entering into the phase 2 and as well as based on our previous experience, like in year 2016 and 2017, especially during month of in third week and second week of the May, we received extreme rainfall events, and which leading to more than 100 fatalities in 2016 and 2017. And based on all this information, we convey this message to the Disaster Management Center. And based on this prediction, they have taken several preparedness measures to prepare the people vulnerable people for worst case scenario. So the two approaches adopted, the national level approach as well as local and community level. And the preparedness meeting was conducted, and all the plans were developed based on association of all stakeholders. And then the lowest administrative division is Grama Niladhari division in Sri Lanka. There are more than 13,000 Grama Niladhari divisions, and next level is divisional secretariat division, where we have 380 divisional secretariat divisions. So all the vulnerable Grama Niladhari divisions and division secretaries divisions. So this hazard and risk analysis were undertaken, and try to identify needs and gaps and planning for deployment of available resources and preparing for contingency plan for worst case likely scenarios. Then we, especially during monsoon forum, we discussed this, and then after that, the monsoon preparedness meeting was conducted by Disaster Management Center. So pre-planning discussions were conducted with military and police, and then district level emergency plans and awareness programs conducted, and then contingency plans processed for all potential divisional secretariat divisions by National Disaster Relief Services Center. Then media campaigns also conducted, especially this Gammadda. Gama is the village in Sinhala, so Gammadda media campaign conducted, and then emergency operation. So we distribute this type of disaster management center distribute this type of leaflets. Aapadawata pera soodanama in Sinhala, that means preparedness before the disaster. And in these leaflets it mentioned like what to do before a disaster and during the disaster and after disaster, and then hotlines to dial during disaster, and especially deployment of search and rescue teams, boats for emergency responses, and conducted mock drills and simulation exercises at district levels and this divisional secretariat levels. So all these preparedness activities conducted, and this based on this S2S prediction. So this preparedness activities as well as early action before the disaster reduced the death toll significantly in May 2018. Thank you very much.
Thank you, Rajeevan. Yes, you have nicely highlighted the case study, and it is not only the warning part, this is preparedness and awareness. This is also a very important component of disaster management, and you have nicely highlighted that part for a case study. Thank you very much.
Thank you.
Any specific questions? Yeah, so I think there is no question in the chat box. So thank you, ma'am.
So
thank
how can I?
Yeah, stop sharing. You can do the stop sharing.
Okay.
Go to the top somewhere and yeah, thank you. Now it is okay. Unshare.
Unshare, right?
Yeah, right now. Yes.
Okay, thank you so much.
Yeah, thank you, ma'am. So I think one talk in that that's Karuna Sagar is not there. So we'll go to the last talk of the session. That is, I can't pronounce this one. Perile Philippe. Okay, it is monitoring.
Thank you.
Yeah, so please go ahead. Monitoring and forecast of interseasonal variability over Africa.
Yeah. So I will share my. Can you hear me properly?
Yeah, I can hear you. Please. Yeah.
Okay. So let me share my screen.
Yes, sure.
Can you see the talk?
Yes.
Okay. So thank you. So I'm going to present you an on a research operational action that Météo France is taking with West African meteorological country. So I work at Météo France at the research centers, and you can see the different partners that we have. The last few years we've been funded by WMO, so which I'd like to thank about this. And so let me start. So the first thing to know is that over West Africa, weather forecast models are not very skillful, and I show you this example of Vogel et al., who shows that basically if you perform a score on daily rainfall with multiple ensemble rainfall versus a climatological reference, you barely do the same in terms of performance, with the score being 0 if it is the greater. So it means that there is a poor skill in terms of rainfall over West Africa. So what we tried to do for the last about 10 years, we developed a strategy to look for predictability in other parameters than rainfall and by post-processing different diagnostics. So this is what I'm going to show, this, first, the overall strategy. So to illustrate this, I show you this time series of rainfall over West Africa, and like many other monsoon regions, you can see that there is a strong temporal variability at specific scales. So over West Africa, compared to some place like India, synoptic variability is very strong and is very key to understand. And it's taking place within quite larger and slower variability that we also want to understand. So basically focused on these 3 scales. So in this action, we decided to look for a specific parameter, mostly, which is precipitable water, which is the vertical integral of water vapor. And basically, we try to use integrated parameters to take advantage of the better representation by forecast models. So in terms of data, we will use ECMWF data, mostly deterministic and subseasonal forecast. And we're going up to the scale of seasonal forecast in this action. So let me show you just a global frame of what we did. Something very important for us is to have a seamless approach that ranges from a large scale, seasonal scale, down to the subseasonal scale, and to finish at the weather scale. And we basically developed the same diagnostic at these 3 scales to allow detect the arrival of subseasonal event and try to take some relevant information from this. Last point, we developed also a very interactive discussion with the West African groups under the forms of a weekly briefing during which we discuss about the situation of the 3 coming weeks and also evaluate the past forecast we did. So this is a very rich part of this project. So a few examples of forecast project that we developed. First, I gave you the website of the MISVA. So this is here. And if you go there, so you have a player with different scales, observation, subseasonal, and seasonal. This is in French so far, but there is an English version that is being developed. And you can see the kind of product you can have. You can have maps of different parameters, time series over different regions. So it's mostly over Africa, but a lot of products are also global, and you can get information also for different countries and different regions. So here's an example of how we proceed. We work first with raw data on the top right, anomalous data on the middle, and to derive precipitation analysis on the bottom. And what you see is that considering precipitable water, you can detect areas where there is enough humidity to trigger precipitation. Regarding the anomalous data, you can see the propagation of perturbations of African easterly wave or different kind of wave. And over West Africa, the specific pattern here, the moist pattern, really matches well the precipitation pattern. So this is what we use, the kind of idea we use. We tracked the moist anomaly above a specific threshold to derive the precipitation pattern. And it works quite well in the end. It performs better than precipitation. Another example that is very important for us is the identification of equatorial waves using Wheeler and Kiladis filtering. So this is available online, basically through a Cartrex website, which uses CEFS model. So we developed the same approach by using ECMWF model, which has very good property of representation of equatorial wave. So basically what you see here, for example, is the propagation of an equatorial Rossby wave around West Africa, which is also consistent here in the CEFS model with a red contour highlighting a moist anomaly. Last thing we developed is a specific project based on precipitable water in which we targeted the critical value that maximize a high skill score depending on different target of precipitation. So basically what I show you here is a difference of score between this product and the precipitation forecast. And how to read that is when it's blue, our product is better. When it's red, the precipitation forecast directly by the model is better. And as you can see over West Africa, for week +1, +2, or +3, the products we developed basically always outperform the forecast of precipitation. So this was done using the Hindcast for different periods. So basically, under the last 20 years, it seems to be very relevant. So to finish, I'll show you a case study on that application. And I'll show you the case study of a wet period that took place during August 2019. And you can see here over different countries, over Senegal at the bottom and Burkina Faso on the top. It's precipitation time series. And you can see this wet anomaly here that followed a dry period. So it's a weekly precipitation on the right. And you see at the daily scale that there were also some extreme precipitation events that took place during this period. And this is observation with anomalous rainfall to the left and precipitable water to the right. And you can see the arrival of this really wet pattern from eastern side and that passed through the western side during these 2 weeks. And it was associated with the arrival of a really large-scale wet bulb coming from the east, and that crosses the West African country. This was associated with an equatorial Rossby wave, and we tried to investigate how soon it was forecast. So basically, when we were doing the forecast, we managed to anticipate this event like 4 weeks ahead, which is quite impressive. And I show you here, so the different forecast time of this event. So at the bottom, you have precipitation anomaly, precipitable water anomaly on the last two right, from S-1 initialization, S-2, week -2, week -3, and week -4. So on precipitation, you can see that this strong anomaly of precipitation was seen about 2 to 3 weeks before the event, while with precipitable water, you can have it almost 4 weeks ahead, which was consistent with between ECMWF and a CEFS model. So this is really the kind of information we wanted to share with you, is that there is predictability with the precipitable water parameter, but also with equatorial wave analysis. This approach also is targeted to a transfer to operational centers. So this is what we did with the National Service of Burkina Faso, and they managed to take over this methodology and issues the bulletin that you can see on the screen for every week with a specific subseasonal forecast for week 2 to week 3. I'm now going to the perspective and conclusion of this talk. So MISVA is a dedicated website for West African forecast, but also global in terms of equatorial wave that goes from synoptic to subseasonal and seasonal scale. It's mostly based on the forecast of climate drivers at different scale, and from this analysis we can get a rich forecast and research discussion that took place during the briefings. In terms of scientific perspective, we have now more than 10 countries working with us, 10 centers, finally ranging from all West Africa. So this is a great potential using these climate drivers with sometimes predictability above 3 to 4 weeks. The integrated seamless approach is very key to us, like understanding the low frequency driven by the ocean and the subseasonal scale. It's something very important to update the seasonal scale. And in the end, multimodal practice also helps getting confidence into the scenario. So having more models with this kind of diagnostic will be a great improvement. Thank you for your attention.
Thank you very much. Yeah, it was really wonderful talk on West African monsoon, the interseasonal variability of that, how it is different from other thing. And you have nicely highlighted your collaborative work with other modeling. So I think if there is questions, we can go for one or two. Otherwise, definitely we will have an interaction with you for any further query on the West African monsoon. Thank you very much. So with this, I think we conclude this session. So I must thank each and every speaker of this session. So it was a really wonderful session, starting from various talk, different parts. Shipra Jain, yeah. Then Ankur Gupta talked about your NCWF system, and the Joyvardhane ma'am, she was just covering how the preparedness and early warning of Sri Lanka, she highlighted very nicely, means for the disaster management. Then Sesagiri Rao Koslu, he also talked about the how equipment office and several model means bias correction modeling efforts they have done. And finally, the last talk is by our colleagues from West African monsoon. So it is a wonderful session. Thank you very much. I think I must thank everybody. So with this, we conclude this today's session in Hall A, and see you again tomorrow morning for the day 4 session, invited talk, parallel talk, and also the poster session. Thank you very much. Goodbye.